In this unit, we're going to be studying thermochemistry. And thermochemistry is the study of chemical reactions through the lens of energy. So we're going to be studying the chemical reactions we already studied, but then also considering changes in energy or in heat that occur as a result of these reactions. In order to fully understand this concept of thermochemistry, however, we would need to understand a number of different concepts with regards to energy. So first of all, what exactly is energy? Well, energy is the capacity to do work or transfer heat. So we need to now define what work is and what heat is. Work is the energy used to cause an object to move against a force. So for example, if you have a gas that's within a container, if you take that container and decrease the volume of the container, you can imagine a syringe. By decreasing the volume of that syringe, you're actually doing work on those gas molecules. So that's a form of energy. The other form of energy that you're even more familiar with is heat. Now, heat is the energy that's used to cause the temperature of an object to increase. So it's that transfer of energy. So for example, if you have a pot of water on a stove, the stove, which is hotter, heats up the water by transferring energy from that hot stove to the water. There are two different types of energy that we'll study throughout this course. The first one is kinetic energy. Now, kinetic energy is the energy of motion. The formula for kinetic energy is that kinetic energy equals 1/2 mv squared. M is the mass, v is the speed. Where we will consider kinetic energy specifically is when we're looking at temperature. We relate kinetic energy and temperature because the faster an object is moving, the higher its temperature is. So they are directly related to one another. They're interrelated. Potential energy is the energy that's stored based on an object's position. You'll look at potential energy quite a bit when you are in a physics class. However, in the context of chemistry, potential energy is the energy that is stored in bonds. It's stored energy that results from the attractive and repulsive forces that an object experiences, and specifically that attractive forces as a result of positive and negative charges. That type of potential energy, we call it electrostatic potential energy. So the attraction that we've already studied between electrons and protons, that is electrostatic potential energy. That is energy that is stored as a result of those attractive forces. So we're going to look quickly at electrostatic potential energy. This formula should look really familiar, and it should look familiar because it's extremely similar to Coulomb's law. Now, if you notice in this equation, we are relating the electrostatic potential energy to the charges, so Q1 and Q2, in addition to the distance between those charges. So if you look at this diagram below, if you look at the top Q1 and Q2, those two blue circles, those two particles have the same charge. And so as a result, if they're extremely close to one another, which is represented at the very top there, the electrostatic potential energy is positive, which means that those two charges are repelling one another. Now, as the distance between those particles increases, the electrostatic potential energy decreases to the point at which it almost reaches zero, meaning there's no attraction or repulsive forces. On the opposite end of things, if you have two particles that have opposite charges, as you can see on the bottom with the red ball and the blue ball, when you start off on this graph, the distance between those particles is extremely small, and therefore the electrostatic potential energy is very negative, meaning that there's a strong attraction between those two particles. As you increase the distance between those particles, the electrostatic potential energy increases until it reaches the point of almost being zero, meaning there is no attraction between those particles. So the more positive the electrostatic potential energy, the more of a repulsive force affecting the particles, while the more negative the electrostatic potential energy, the more attractive forces. Now that we've talked about different types of energy that we'll be looking at in this unit and further on in this class, we need to talk about units of energy. So we talked about the conceptual concept of energy. Now let's talk a little bit more quantitatively. Units for energy include joules. The unit abbreviation is just a capital J. And calories. Now, the term calories might be familiar. We'll look at that in just 1 second. The relationship between joules and calories is that 1 calorie equals 4.184 joules. Now we've heard the term calorie, however, the calorie that we consume on a daily basis, that is not the lowercase cal. Instead, it's a capital CAL, which represents 1,000 of the calories that we consider in this course. Now that we've talked about the concepts of energy, we're going to start talking about the transfer of that energy, but in order to do that, we have to understand the movement and where that energy is going to be moving from and to. So we have 2 terms. We have the system and we have the surroundings. So if you look at this diagram right here, the system in this case is H2 and O2, which means the system is what we choose to study. So it's the substances we choose to study. It tends to be the reaction that we're concerned with, the reactants and the product. So in this case, it's just H2 and O2. The surroundings are everything else. So in this case, it would include the cylinder, the piston, and everything else beyond that. Let's talk about the first law of thermodynamics, which is going to have a large impact on our work throughout the rest of this unit. The first law of thermodynamics states that energy can neither be created nor destroyed. So in order to fully understand the first law of thermodynamics, I have to give you one more definition, and that's internal energy. A system's internal energy is the sum of all of the potential and kinetic energies of its components. So when we're talking about the first law of thermodynamics, if you look at this diagram here, what it shows you is changes in the internal energy. So if you look up the left-hand side with the blue arrow moving downwards, what that shows you is that the initial internal energy is higher than the final internal energy. So what that means is that the system lost energy while the surroundings gain energy. That statement right there, that the system, when it loses energy, that the surroundings gain that internal energy, that is the first law of thermodynamics. You can't create or destroy energy. It has to go somewhere. So the way that we represent that, the loss of energy from the system, is with a delta E, delta meaning change in internal energy that is negative. If you look on the right-hand side, the initial internal energy is lower than the final internal energy, which means that the system gained internal energy while the surroundings lost energy. And that change in internal energy, therefore, is going to be positive because the system gained internal energy. Here's another representation of this. The fact that the initial internal energy is higher than the final internal energy means that energy was lost by the system, and therefore your delta E is going to be less than 0. It's going to be negative. We're now going to start talking about reactions and considering the energy that is involved in those chemical processes. Reactions can either be endothermic processes or they can be exothermic processes. In an endothermic process, the system absorbs heat, so the delta E is going to be positive. The change in internal energy will be positive, while in an exothermic process, the system is going to lose heat, meaning that the change in internal energy will be negative. So in this example, it provides you with the opportunity to write reactions and to incorporate the concept of internal energy or heat into this concept. So in this example, it tells you that sodium hydroxide is dissolved into water and that the temperature of the water increases. So the first thing that we have to do is we have to write the equation for this reaction. So NaOH, which is a solid, is going to be dissolved, and it's going to, because it's a strong base, it's going to dissolve into sodium ions and hydroxide ions. Now, this is a dissociation reaction in which NaOH is being dissolved. And if you notice, it asks us to describe the heat flow. So heat is being lost from the system from NaOH and enters the surroundings, the water, and you know that because the temperature of the water increases. So since the system loses energy, what that means is this is an exothermic reaction. To represent an exothermic reaction in an equation, we put the heat on the right-hand side, on the product side, because it is being released, it's being produced. So we represent it that way. If you have an endothermic reaction, you would place the heat on the reactant side because it is being put into the system. The last concept that I need to talk about is state functions. A state function is one that depends only on the difference between initial and final states, not on the path that was required to get there. So change in internal energy, that is a state function. So let me explain why. If you look at this real-world example, it shows you a battery losing energy. Now, there are two different ways that it can lose energy. Notice in A, it loses energy through heat, while in B, it loses energy through heat and through work. If you look at the graph below at that diagram, it shows that the total loss of energy from the battery is the same whether or not it's just lost as heat or if it's lost as heat and work. And so this is going to be extremely important to us as we look at additional concepts such as Hess's law. The fact that how you get there doesn't matter, simply the difference between where you started and where you finish.